Problems of empiricism. The structure of science. One science, says Professor Nagel, one takes its ultimate point of departure from problems suggested by observing things and events encountered in actual experience. 78. It aims to understand these observable things by discovering some systematic order in them, i.e. by explaining them. 78. It is this desire for explanations which are at once systematic and controlled by factual evidence that generates science. 4. See also 15. Understanding the structure of science, therefore, means understanding the structure of scientific explanations. 15. The view of explanation set forth by Nagel does not differ in any essential respect from the hypothetico-deductive account. However, a considerable amount of detail is added. In what follows I shall deal with the distinction drawn between experimental laws and theories, ch. 5, the cognitive status of theories, 6, the explanation of established theories, laws, by other theories, ch. 11, and with Nagel's general views concerning the structure of science. Two theories are distinguished from experimental laws because they employ terms like molecule which ostensibly designate nothing observable. 80. The distinction does not mean that laws are more highly confirmed than theories, or that theories are entirely speculative. 80. Nor is it assumed that experimental laws express relations between data apprehended directly or non-inferentially through various sense organs. 81, 122. The vagueness of the term observable. 83, 90. The difficulty of proposing a precise criterion distinguishing theories and experimental laws are duly acknowledged. Yet the inference that the distinction is spurious because it is vague is rejected by asserting several well-marked features differentiating the former from the latter. 83. These several features essentially boil down to one: each descriptive term in an experimental law is associated with at least one overt procedure for predicating it to some observationally identifiable trait when certain specified circumstances are realized. 83. This feature connects with others, viz. I. The meaning of the descriptive terms of experimental laws, the so-called observational terms, is partly fixed by the procedure. Hence, 2. An experimental law, unlike a ethical statement, invariably possesses a determinate empirical content. 83. 3. Experimental laws but not theories can be the result of inductive generalizations. 85. 4. To the extent to which they are connected with operational procedures, the content of experimental law is independent of any theory that might be used for their explanation. It also must be independent, the law must be intelligible, and must be capable of being established, without reference to the meanings associated with it because of its being explained by some theory. Indeed, were this not the case for the laws which a given theory purportedly explains, there would be nothing for the theory to explain. 87. Hence, an experimental law has a life of its own, not contingent on the continued life of any particular theory that may explain the law. 87. Theories are analyzed into a. An abstract calculus whose postulates assert nothing since they are statement forms rather than statements. 91. But implicitly define the basic notions of the system. 90. 160. b. Correspondence rules, relating theoretical notions to observational procedures. 94. Or experimental concepts. 95. Such rules make it possible to use the theory as an instrument of explanation and prediction. 93, 106, and to investigate its material truth or falsity. 222. Without correspondence rules a theory is not even a statement. 141, as its descriptive terms, or rather those for which no rules of correspondence are given, have the status of variables. 132, 95. Finally, c. A theory contains a model. A model is defined relative to the abstract calculus and consists in a specification of its postulates that turns them into true statements and preserves the logical relations between them. 96, n.4. A model in this sense need not provide correspondence rules. 95, 97, although it can suggest at what point such rules may be introduced. 113. Nor does a model turn the postulates into statements and the theoretical terms into constants. 132. For while it might contain constants only, it is not the only possible model. 97. This also explains why even overwhelming evidence for a theory may not be assessed as sufficient for asserting the physical existence of various elements in the substantive model in terms of which the theory is formulated. 117. The calculus, the correspondence rules, the models must not be construed as separate items, introduced in succession at various stages in the actual construction of theories, but simply as features that can be isolated for purposes of analysis. 106f. 3. Now it appears that these features can also be isolated in the case of experimental laws and, more generally, in the case of any set of observation statements that possesses suitable closure properties. Observational terms are associated with overt procedures for predicating them of observationally identifiable traits or with ostensive rules, as we shall call them. 2. Theoretical. 54. Terms are related by correspondence rules to observation terms, which in turn are related to observable traits by ostensive rules. Separating the theoretical terms from the correspondence rules leaves an uninterpreted system which can be expressed in the form of a calculus CT with postulates PT. 91. Separating the observation terms from the ostensive rules leaves again an uninterpreted system which can also be expressed in the form of a calculus CO with postulates PO. The objection that the logic of the observation terms is completely determined by the ostensive rules cannot be raised by Nagel, who rejects sense data. 88, 122, who asserts quite explicitly that ostensive rules define a partial meaning only. 88, and who points out that already common sense involves the use of abstract conceptions. 11. The further objection that the logical structure of the observation language is hardly ever available in the form of explicit principles overlooks that the same is true of theories also. Here too, the explicitly formulated laws mirror only part of the logical relations in which the terms stand to one another, the remainder must be unearthed by attending to the way in which theoretical terms are being used. It is plausible to assume that many theoretical postulates have originally been obtained in this manner. Examples: the Archimedean postulate in geometry, the law of excluded middle. In the case of observation languages this applied to all postulates. This is the only difference. Finally, there will be models for PO. The most familiar models of course assume things having certain properties, but we need not restrict ourselves to them. We may use models similar to those introduced by Whitehead in the case of geometry, and even more unfamiliar ones. There emerges therefore a complete parallelism, in all the respects examined by Professor Nagel, between the domain of observation and the domain of theories. Let us examine the consequences of this parallelism. For it is often said that the aim of science is the classification and the prediction of observational results, and that the distinctive characteristic of modern science is mathematics and the experimental method. This is correct as a first approximation, but one has to add that experiments are used not only for discovering new facts, but also for revealing the detailed structure of facts already known. This is what really distinguishes modern science from its predecessor. The laws and descriptions of the Aristotelian science were supposed to give an account of observationally identifiable traits exactly as they appeared to the observer, cf. the famous example of the drop of wine in 10,000 pails of water, De General Etcorr, 328-27. The point of view of Galileo and Newton, which was prepared by the ancient atomists, aims at an analysis of such traits that first eliminates the contribution of the observer and then tries to show how the remainder results from an interplay of processes which can be isolated only with difficulty, or perhaps not at all, and which will have to be described by theories in Nagel's account. 55. See already here that the familiar characterization of science as an enterprise that aims to understand observable things by discovering a systematic order in them, Nagel, 78, is still quite Aristotelian, especially if we take it together with the remark that observational laws and observational notions have a life of their own. 87. And we anticipate that a different account will have to be given of the role of observation and experiment. A science that is interested in analysis uses theories for describing the hidden processes which constitute the observable traits. Such theories must be rich enough to express the specific features of the individual processes, and they must also be capable of giving an account of the manner in which all these processes collaborate and bring about the overt traits and observational facts to be analyzed. In other words, they must provide statements and laws suitable for expressing such facts. Of course, the statements need not repeat what was said about the facts at an earlier time. Nor is it advisable that they should. The earlier formulations will usually contain the gross reactions of the observer and the crude beliefs emerging from them, and it is just such beliefs one wants to exclude. All that is needed is that the order introduced into the observable material by the theory be comparable, both in complexity and in effectiveness, with the order established by the concepts and laws already in use. The exact form of the order need not be preserved. Thus the explanation of Kepler's first law by the general theory of relativity, Schwarzschild's solution, does not give us an exact ellipse, nor are the predicates describing the shape those of ordinary physical geometry. They do not even share a core of meaning with the preceding notions. 3. Yet the descriptive apparatus of the explanation can compete well with that of the older astronomy. It is even preferable, as it no longer contains the incorrect assumption of a spatio-temporal structure that is independent of the state of motion of the observer. It follows, then, that a satisfactory theory contains a calculus C and postulates P degree which, though not coinciding with Co and Po, can yet provide just as effective a logical skeleton for an observation language. Let us return to Professor Nagel's account. In this account the ostensive rules are applied to the descriptive terms of Co, the terms of CT, C. Included, get their interpretation only indirectly, with the help of correspondence rules. What has just been said would seem to suggest that CT should perhaps be interpreted in a more direct fashion, without the detour through Co and correspondence rules. There is no reason why the overt procedures which according to Nagel are used to fix a definite, if only partial, meaning for the descriptive terms of Co should not be applied to the descriptive terms of C, and in this way fix a definite, if only partial, meaning for them. The remainder of the theory would receive its content not through additional linkages, added from without, but via the deductive relations between PT, CT, and P, C. Co, PO and correspondence rules would be superfluous. For example, one might apply the operations usually employed for giving content to the term heavier than of some commonly understood idiom to the term possessing much greater relativistic mass than of the special, or the general theory of relativity. This direct method of interpretation, as we shall call it, would seem to reflect much better the features of a science that progresses by analysis than does Nagel's method. It avoids unnecessary duplication of terms and relational systems, Co with Po versus C, with P degree. It prevents the perennial retention of the errors implicit in the older observational idiom, e.g. it prevents the perennial retention of a language that is not Lorentz invariant, or of a language of mental terms that does not allow for the incorporation of materialistic features. The charge of circularity which Nagel might raise and the related charge that such a decisive change of the observation language may leave nothing for the theory to explain, 87, counts little in comparison with such advantages. Besides, it adds another point in favor of the direct method. For the need to change the observation language indicates that there was no explanandum to start with, or at least, that the older experimental laws were not the proper explanandum. What did need explanation was how people could believe them, but this is an altogether different matter. 5. Nagel's views on the interpretation of theories are closely connected with his account of a reduction, which is the explanation of a theory, or a set of experimental laws established in one area of inquiry, the so-called secondary science, by a theory usually, though not invariably, formulated for some other domain, the primary science. 338. The most striking cases of reduction are those where a set of distinctive traits of some subject matter is assimilated with what is patently a set of quite dissimilar traits. 339f. In these cases the laws of the secondary science contain terms that do not occur in the theoretical assumptions of the primary discipline. 352. A reduction will now be possible only if special hypotheses, connecting the dissimilar terms of both disciplines are used in addition to the principles of the primary science. 365, 353f. The existence of these hypotheses must not be understood as expressing an ontological hiatus. 365, or some experimental, or even metaphysical facts about some allegedly inherent properties of objects. 369. It rather expresses the logical fact that the terms of two sets of statements stand in certain relations to each other. 369. The content of the connecting hypotheses depends on the context in which a reduction is to be achieved. 357. The principles of the primary science may be connected with experimental notions by these hypotheses only. They cannot then be checked by experiment, but function as coordinating. 57. Definitions. 356, Case 1. On the other hand, the principles of the primary science may have been interpreted independently of, and perhaps already before, the secondary science. The reduction of thermodynamics to mechanics is an example of this kind. In this case, the expressions belonging to both the principles of the primary and the secondary science possess meanings that are fixed by their own procedures of explication, and are intelligible in terms of the rules or habits of usage of the corresponding branch of inquiry, and when those expressions are used in that branch of study, they must be understood in the senses associated with them in that branch, whether or not the science has been reduced to some other discipline. 352, a repetition, on a higher level, of the remark about the independent life of experimental laws. Clearly the connecting hypothesis will now be one that does not hold as a matter of definition, and will not be one for which logical necessity can be claimed. 358, Case 2. Most reductions are supposed to be of this kind. Thus the reduction of thermodynamics to mechanics, or of chemistry to contemporary physical theory does not wipe out, or transform into something insubstantial, or merely apparent the distinctions and types of behavior which the secondary discipline recognizes, nor does the reduction of headache to neurophysiology establish a logically necessary connection between the occurrences of headaches and the occurrence of certain events and processes specified by physics, chemistry, and physiology. 366. The doctrine of emergence, to mention another case to which the above considerations are applied, is on firm ground when construed as a thesis concerning the logical relations between statements describing the emerging traits and statements of the quite different theory used to explain their emergence. 372. And so is organismic biology insofar as it asserts that connecting hypotheses linking biological terms to terms of physics are necessary for a reduction, but are not yet available. 434. 6. From these remarks there now emerges the following view of the structure and, possibly, the development of science. In so far as they can be related to each other, the explanatory systems, or the theories of science, are arranged in layers, or levels, starting with an observational level and moving up to levels of increasing abstraction. Each level is self-contained, having methods and procedures of its own. 352, it gives rise to an equally self-contained domain of knowledge. The layers are linked by rules of correspondence with the observational level, 93 feet, whose laws have a life of their own, not contingent on the continued life of any particular theory that may explain them. 87. In addition, the layers may be connected with each other by specific hypotheses. 365, 473. The rules of correspondence give empirical content. 90, 166, 300, and they also make possible the explanation of observable phenomena. 93,97, which are the ultimate points of departure for scientific thought. 79. Connections between layers are necessary if lower levels are to be explained by, or reduced to, the higher levels. As we have seen, such explanation neither wipe S out nor transform S into something insubstantial. The level explained, 366. It leaves intact the self-contained character of each level, and the relative independence of each domain of knowledge. Now if we take it for granted, as does Nagel, that explanation is essential for science, 3, if we assume that it is the desire for explanations which generates science, 4, then the above arrangement of layers becomes a model not only of the end result, but also of the development of our knowledge. The development of knowledge then consists in the accumulation of facts, and of theoretical layers. Science advances by internal improvement of each level, by addition of new facts on the observation level, by addition of new explanatory systems on top. There may of course be a considerable amount of change preceding the establishment of each single layer. Theories may have been formulated tentatively, and may again have been abandoned. But as soon as a theory is established in one area of inquiry, 138, as soon as it starts pervading this area with its methods and its specific terminology, in the very same moment it assumes the independence of procedures and rules of usage that we have reported above. The lower levels then actually become somewhat assimilated to the observational language, and their abstract conceptions assume a similar life of their own. Here, then, we have the outlines of what one might call the layer model of scientific knowledge. 7. This ingenious model, which tries to combine the empiricist's concern for facts with the realization of the importance of theories, and which also tries to satisfy the wish for some amount of stability, is in agreement neither with actual science, nor with reasonable methodological demands. The reasons for this have already been stated, although so far they have been restricted to the relation between theories on the one hand and experimental laws and observation languages on the other. It has been pointed out that Nagel's method involves an unnecessary duplication of relational systems. And it was suggested that the ostensive rules which connect terms with overt operations and traits should be linked to the theories directly, and not via an older observation language and correspondence rules. In this way the older observation language would be abandoned and its abstract concepts replaced by the abstract concepts of the theory. The charge of circularity was answered by showing that the non-circular procedure preserves, at least part of, the structure of the observational laws and thereby removes it from the domain of criticism. This point deserves repetition. If it is the business of science to explain, if explanation takes its ultimate point of departure from problems suggested by observing things and events in common experience, 79, if the description of these things is allowed to 59. Have a life of its own, 87, that can be expressed independently of any theory, 86, if a change of theory changes only the theoretical interpretation of the experimental laws and observational terms, but leaves unchanged another part of their meaning, 87, then the relations between terms which constitute this observational core will forever be exempted from change. Their stability will be guaranteed not because a detailed examination has found them to be adequate. Nagel admits that empirical laws may be as speculative as theories, 80, but because they have been arranged in such a manner that an examination becomes impossible. They have been turned into veritable idola for it. And such idola can be criticized only by a procedure that permits us to compare them with other relational systems, for example with the observation languages which universal theories give on direct interpretation. Such a comparison, though being perhaps circular, is thereby shown to have a definite advantage over and above the method described by Nagel. Now in the case of reduction the situation is exactly the same. But it is somewhat easier to present it in an acceptable manner. Assume for that purpose that we are dealing with the explanation of classical, Newtonian, momentum conservation by the special theory of relativity. Nagel himself regards the relativistic notion of mass as a new notion, and he points out that the conservation principles must be reformulated in terms of relativistic mass, 111. He gives a brief, though very enlightening, account of the manner in which the relativistic concept differs from the classical concept, 170. Newtonian mass is an intrinsic property and it is additive. Relativistic mass is a function of the relative velocity, and it is non-additive. True, he seems to be inclined to restrict the modification to particles moving with great speed. The mass of a particle moving with great speed varies with the velocity, so that the classical principle of conservation of momentum does not appear to hold for such principles. 111, my italics, but I do not think that this passage should be interpreted as saying that the dependence on velocity disappears at low speeds, although it is of course to be admitted that it can no longer be observed at low speeds. Now the first thing we note is that at low speeds, and after omission of effects unlikely to be spotted experimentally, the theory of relativity gives exactly the same predictions as does Newton's theory, and we also obtain a sentence similar in syntactical structure to the standard formulation of Newtonian momentum conservation. 358, my italics, the reference is to the reduction of thermodynamics. In the domain in question, V1, the theory of relativity is therefore as effective a predictive device as is the older point of view. But of course, the similar syntactical structure has a meaning that is unmistakably different from what Newtonian momentum conservation asserts. 358, the reference is again to thermodynamics. This follows from what was said above. The theory of relativity uses the relativistic notion of mass, dependence on v/c, non-additivity, under all circumstances, and not only for velocities comparable with the velocity of light, although for v/c1 the predictions, i.e. the numbers, resulting from such use will be indistinguishable from the numbers produced with the help of the classical terms. We see then that the theory of relativity can do everything the classical theory can do, that it can do a few more things, and that it is successful where classical physics fails. And it would seem that we can safely abandon the classical point of view and live with relativity instead. Of course this does not mean, as has sometimes been suggested, that we shall abandon the splendid mathematical machinery of classical celestial mechanics and that we shall regard the achievements of this discipline as being of historical interest only. Abandoning classical physics means abandoning the classical concepts. The classical formulae may be retained. For however, this is just the procedure which encounters Nagel's objection. It may be granted by the objection that we have made some progress. But an explanation of classical mechanics has not been achieved. Such an explanation demands the continued use of the classical concepts, cf. the argument at the bottom of p. 357, as well as the presentation in section 5. Let us now examine this objection. The objection is based on the following two assumptions: I. Science proceeds by explanation. 2. The explanation of well-established laws is by deduction. From these assumptions it is inferred that there must be special hypotheses, cf. section 5, connecting the relativistic notions with the classical notions. Using these hypotheses we obtain pairs of theories whose elements are capable of making predictions in a certain domain, one of them being capable of making predictions in other domains also. The first question that arises is why science should be cluttered up with double systems of this kind when one half can do the job of both. The second question concerns the connecting hypotheses themselves. Here we must distinguish what we earlier called case 1 and case 2, section 5. Case 1 means now explaining relativistic mass in terms of classical mass, which certainly is not in accordance with Einstein's intentions, though it may be in accordance with the original intentions of Lorentz. Another example will make the situation even clearer: the phlogiston theory, especially in the form in which it was developed by Stahl, and the new ideas of calcination and oxidation form a perfect pair for reduction. It does not matter that the phlogiston theory has now been abandoned, quite the contrary, this is an argument in favor of our procedure. What does matter is that at the time in question it was well established and, because of Stahl's particular 6L prejudices, thoroughly observational. The method discussed at the present moment would amount to retaining the notion of phlogiston and the theoretical context surrounding it. The expressions belonging to a science possess meanings that are fixed by its own procedures. Whether or not the science has been reduced to some other discipline, 352, interpreting all the new notions by reference to it. It would amount to saying that new conditions for the production and transfer of phlogiston had been discovered, Cf. the similar locution in the case of headache, 366. However, we prefer to say that the notion of phlogiston had turned out to be inadequate and that we had found reasons to abandon it. Case 2 assumes that the special hypotheses connecting classical terms and relativistic terms are empirical statements asserting that the occurrence of the state of affairs signified by a certain theoretical expression in the primary science is a sufficient, or a necessary and sufficient, condition for the state of affairs designated by an expression in the secondary science, 354. In the present case they would assert that whenever a certain relativistic state of affairs is realized, intrinsic mass that is additive, cf 170, is present also. But the theory of relativity roundly denies the existence of intrinsic masses and therefore contradicts the hypothesis. Again, the method recommended by Nagel leads to undesirable consequences. Now this method follows from assumptions, I, and, 2, concerning explanation. The fact that it leads to undesirable consequences shows that at least one of the assumptions is in need of change. We shall either have to admit that science does not proceed by explanation, or that explanation, or reduction, is not by deduction. As far as I am concerned, the problems as to which way to choose has no interest whatever. If we know how science proceeds, if we know what moves can be recommended as reasonable, then we know all we need to know. The question as to how these reasonable moves should be described is a problem for the publicity experts and should perhaps best be settled by introducing a new terminology that is not as loaded as is the term to explain. 8. Our argument is still incomplete. Nagel assumes that the laws of the secondary science have been established in some area of inquiry, 338, so that they agree with the experimental results in this area. Now while classical mechanics satisfies this condition, the area of inquiry being defined, relative to special relativity, by v/c⁻1, it is refuted by experiments outside, 3. The same is true of the example which Nagel himself uses, viz. the reduction of thermodynamics to mechanics. Here, too, there exist experimental results, Brownian motion, which contradict the secondary science. Moreover, the existence of such common phenomena as noise would seem to show that the domain of success of the secondary science is really quite small. 5. Now, in order to dispel the impression that my argument against Nagel succeeds only because he has chosen his examples badly and that it depends on whether or not the secondary science is adequate, I shall assume in the present section that it is and that no exception has been found. Can Nagel's theory of reduction be retained under these quite unrealistically ideal circumstances? I think it cannot. The reasons are as follows. One of the most important tasks of science is to test the laws and the theories it introduces for the purpose of explanation and analysis. This cannot always be achieved by a direct comparison with facts. Some of the most decisive refuting instances for a theory T are produced with the help of alternative theories T which contradict T, repeat the success of T, make predictions in new domains, at least some of which are then confirmed by phenomena P. We may say in such cases that T has been indirectly refuted by P. The refutation of thermodynamics by Brownian motion is of exactly this kind. Moreover, it can be shown in this case as well as in others that the alternative T is essential, since a direct refutation of the P, of thermodynamics by Brownian motion, is excluded by physical laws. 6. Now pairs of theories such as T and T are ideal candidates for reduction, and this according to Nagel's own criteria. In reducing T to T, Nagel would interpret them in a manner that removes the inconsistency. This follows from his general views on reduction as well as from his own example, the reduction of thermodynamics to mechanics. We have shown above that such interpretations frequently run counter to the intentions of the proponents of T and V. We have also mentioned other disadvantages. We now see that the procedure lowers the empirical content of our knowledge by eliminating valuable tests. It is therefore consistent neither with actual science, nor with reasonable methodology. In the meantime, I have been informed by Professor Smart that Nagel is prepared to admit the inconsistency of many theories he regards as candidates for reduction, and that he suggests construing the connecting hypotheses as probability hypotheses. This does not at all improve things. Firstly, because the remark concerning the unnecessary multiplication of explanatory systems still remains in force. Secondly, the theory of relativity, to mention only one example, excludes intrinsic mass not only with high probability, but always. See the argument in section 7, case 2. Thirdly, a weakening of the inconsistency between competing theories would reduce the critical ability of both and must therefore be avoided. No amount of small-scale adaptation will do. Nagel's theory of explanation must be altogether rejected. 9. We now come to the last item on our list, the question of the cognitive status of theories. It is impossible to treat here in detail all the arguments and interesting observations which Nagel presents on this problem. I only want to make 2 points. First, Nagel points out that a defender of either view, realism or instrumentalism, can not only cite eminent authority to support his position, with a little dialectical ingenuity he can usually remove the sting from apparently grave objectives. And he concludes that once both positions are so stated that each can meet the prima facie difficulties it faces, the question as to which of them is the correct position has only terminological interest. 141, in brief, the opposition between these views is a conflict over preferred modes of speech. 152. Now it is certainly correct that much of the contemporary discussion of the issue has precisely the character described by Nagel. It is also obvious that the addition of further ad hoc hypotheses may remove the still remaining differences. But when comparing philosophical theories, or physical theories, we should not use their degenerate forms but those formulations of them which contain only a minimum of adaptive measures. And there are versions of realism and instrumentalism which satisfy this demand. The instrumentalist version of the idea of the motion of the earth, to take one of the most important examples, was supported by the argument that a real motion of the earth would contradict the highly confirmed laws of the Aristotelian science of dynamics. The instrumentalistic version of Newton's theory of gravitation was already defended by Newton himself on the grounds that experience had shown matter to be inert so that it could not be regarded as a seat of forces. A realistic interpretation of the quantum theory is rejected on the grounds that it is inconsistent with the conservation laws and the laws of interference. These are strong reasons, and they can be removed only by arguments showing that it is desirable to introduce theories which contradict already existing laws. In the last section we have indicated that such arguments can be provided. This removes one of the most serious historical objections to realism. The second point I want to make is connected with the usual debates concerning the distinction between observation terms and theoretical terms. As has been reported in section 2, Nagel objects to regarding the distinction as spurious because it is vague. 83. This is certainly a valid point unless the raison d'etre of the distinction consists in the role it plays in arguments about matters which do not admit of gradual transitions. In this case, proof of the vagueness of the distinction is proof of its irrelevance. Now, one of the most important reasons for making the distinction, and the reason for a thinker like Berkeley, is that one wants to know what is established, and what therefore can be known to exist, and what is hypothetical only. We take it for granted that observable things can exist, whereas some would claim that ascribing existence to theoretical entities is not only false, but a logical blunder. Now, the distinction between existence and non-existence certainly is not a gradual one. Admitting that observability is a vague concept is therefore tantamount to admitting that the problem as to what exists and what does not is independent of it, that it is a metaphysical problem, and that the question as to what can be observed and what cannot be observed is comparatively unimportant. Exactly the same result is obtained by attending to what has been said in section 3. In this section we pointed out that observation languages which are not sense data languages, which contain abstract notions, and whose use amounts to asserting certain relations, can be dealt with along exactly the same lines as theories. There will be a calculus, co with postulates po, and there will also be models. It follows, then, that even the greatest success of the observation language may not be assessed as sufficient for asserting the physical existence of the various elements in the substantive model in terms of which the observation language is formulated. 117, applied to theories. Not even the existence of observable events is therefore assured, and the problem of the cognitive status of theories expands into the problem of the cognitive status of all notions of our language. Nagel's book contains hardly a hint concerning this more general problem, and this despite the fact that his own analysis of theories and his rejection of sense data leads straight to it. This is true of other accounts also. The ontological status of observation terms is a matter that is hardly examined today. 7. This certainly is a step back from the sophistication that had already been reached by Kant, and an indication that the belief in sense data, though denied in words, still seems to have a strong influence upon the deeds of almost all contemporary philosophers of science. 10. The topics dealt with so far fill hardly 1/3 of Nagel's book. There are chapters on the quantum theory, on the science of mechanics, and there is a large amount of argument dealing with the social sciences. These arguments are very instructive, and I am sure that everyone reading the book will greatly profit from examining them. The reason why I have concentrated on the chapters of the book dealing with more general matters is that the opinions expressed there are widespread, that they are presented in great detail, and supported with better arguments than I have found elsewhere.